systems of equations. We're going to look at some special cases today. Now, don't lose sight of the three ways that we've been able to solve systems of equations. What was the first way that we looked at solving systems of equations? Okay, substitution's one method. What was another method? Say it again. Elimination. And then the third one was the very first one that we looked at. We used decimals a lot for it. A lot of linear equations that ended up in a graph, didn't they? Ended up in a graph. We were looking for where lines cross. Remember those three things? So don't lose sight of that. Solving systems of equations can be done graphically, looking for a point where the lines crossed. Used by substitution, get a variable alone. Or now this new part that we've talked about, elimination, to be able to eliminate one variable and solve for another. Now today, there's going to be cases today where some weird things start happening with systems of equations. And I think that if you can just remember all your rules to apply, you'll be in good shape. So what we want to ask ourselves today is this. Can a system of equations have, what's the phrase right here? No solution or many solutions? That's the question we're going to ask right here. Okay, and since it is a question, I should probably learn to punctuate a little better and put a question mark down here at the end. Okay? All right, so goals to this for us. First goal, determine the number of solutions to a system of equations. Okay? We're used to finding a solution, 4, 7, 3, 2, 1, 6. That type of stuff, right? Ordered pairs. Today, things are going to change up a little bit. There will be times when you get an ordered pair, but not all the time in this section. And then the second thing, goal-wise, we want to look at using linear systems to solve real-life problems. All right, vocab-wise. One of my favorite jokes is parallel lines have so much in common, it's a shame they'll never meet. All right, Chelsea's looking at me like, you say that one more time. All right, well, if I had to ask you guys to come up with a definition of parallel lines, what would you tell me? They're never going to cross. Two lines that never cross. All right, so I'm going to jot this down. Two lines that never cross. Two lines that never cross. Now, guys, in the past, we talked about writing equations for lines given some conditions. And there was a characteristic that involved slope as it related to parallel lines. You guys remember what the rule was about the slopes of lines that were parallel? The value of their slope, maybe I should say? They were the same. Okay, everybody agree with that? Slopes were the same. So I'm going to jot that down just as my memory serves me. Slopes are the same. So if I had to make a drawing of parallel lines maybe in my box over here, this is what it might look like. Yes? Oh, yeah, I'll get it. Parallel lines look like this. Here's a line. Yeah. Those look parallel to you? Okay, and one thing I need to change right here is the following. Forgot the word never in here. So you might, whoops, two lines that won't cross. I'll squeeze it in here. Maybe. It's two lines that do not cross, all right? My mistake. So you're going to hear an awful lot about parallel lines in this section. If parallel lines don't cross, can they have a shared point? And if systems of equations have dealt with sharing of points or the point where lines cross, what are you going to say about the solution for parallel lines? Not going to be one. Okay, and we'll look at this here in a second. Second thing you're going to hear me talk about is consistent lines. Two lines that are consistent. Sometimes I'll say consistent, dependent, but consistent is really the word you need to know. Basically what that means is this. One line, there's my problem. One line on top of another. It's It's kind of hard to read. Come on. One line on top of another. And it's one line on top of another. Guys, if one line's on top of another, what's going to be true about their slopes? It's the same slope, but it's the same line. Okay, so basically what this means is it's just the same line. How many points are shared if I take one line and drop another line? All of them. So how many number of solutions for consistent systems do you think? Going to be many, all right? So the things that I want you to hear about today are this. If I say parallel lines, how many solutions? The parallel lines are unique? No. No shared point, no solution. How about consistent lines? One line right on top of another. No solution or many solutions? Many solutions. So that's kind of the answer to the question, okay? And I've got a table that we'll put down there to fill that information in. But understand what parallel lines are and understand what consistent lines are, okay? All right, kiddos, so here's what's really important today for us. We need to recall some slope-intercept form, all right? Now, again, I've always said this, if you run into a pinch, okay, if you run into something that you're not sure of, your last resort should be check out what? Decimals. At least get a visual of it so you can kind of work your way through it from there, all right? So don't forget decimals and all this. I believe you guys have a line right in the middle here of the table, don't you? Okay. Things to recall for this section, I think it'll be okay. Recall slope-intercept form. Slope-intercept form, which variable is always going to be alone? Y is always going to be alone. Check this first equation out. Is that in slope-intercept form?
Yeah.
Okay, so do we need to rewrite it in slope-intercept form? No. No. What's M represent again? Slope, right? So looking at this equation right here, y equals 3x plus 4, what is my slope? Okay, just the value, 3. Fraction formula would mean rise 3, run. That's track practice. Run 1 is what I meant for math. I didn't say run. That's track practice. Okay. You got my mind on track already. I have had my coffee. Peppermint mocha. It's good stuff this morning. Okay. How about the y-intercept here, kiddos? What's that value? Where are we going to start? 4. Okay. So B represents the y-intercept. The intercept's 4. Second equation. In slope-intercept form? No. Let's rewrite it so it is in slope-intercept form. Let's get y alone. So what do you have to move out of here, kiddos? The 3x. So if the 3x is positive on the left, what shall it be on the right? Negative. So to get y alone here, I'm going to say, hey, you know what? This is the same as y equals negative 3x plus what? No, 4. Negative 3x plus 4. How about your slope here then? Negative 3. McKenna, what's the intercept? 4. Great. Third equation right down there. Slope-intercept form or not slope-intercept form? Not. Got to get y alone. So the first thing we need to move out is an x. So I'm going to do some work down here. You guys agree 3y would equal negative 2x plus 9 when I do that? Whoops, I'm ahead of myself. If I've moved that if I move the 2x to the right side, wouldn't it be negative on the right here? What do you want to divide everything by, kiddos? 3. Divide everything by 3. So you're going to end up with y equals, let's see, negative 2 over 3. Is that going to divide nicely, or should we leave it? So we'll call it negative 2/3 x. How about the 9 divided by the 3? Plus 3 then, right? Again, y is alone. That would kind of go back to your substitution part right there. Once you've established that y is alone, what is your slope? Negative 2/3. Good. How about your intercept? 3. So again, I know that's stuff that we've hammered a lot. Just a quick recall on that. You know how to get something in the slope-intercept form, identify the slope and the intercept? It's going to be very important for answering what we're going to do today. Good to go? Any questions so far? So guys, here's a visual of what graphs of solutions can look like. Guys, We in the past have looked at lines where lines did this. They crossed. And this one point right here was considered my solution, right there. That one point was considered my solution. So how many solutions, or how many points, the lines that cross, how many points do they meet at? Just 1 point, okay? So any lines that cross like this is going to be a situation where you only have one solution. Okay? We already talked about parallel lines. If you have two lines that look like this, we have this line and this line. Parallel, right? Never going to meet? Solution or not? No solution. No solution. Oh, no solution. No solution. Kind of like the Raiders defense on Sunday. No solution for the Viking offense. Boom! That's when I was back as barley mouth. Alright. I better shut up if I'm going to lose on Sunday now. And then in which case I'll come back to the perfect Hawkeyes. Okay? Alright. Tell your mom the Hawkeyes are 10-0, by the way. She won't hear it. Last thing we have, guys, is something like this. There's a line, and then right on top of this is another line. I'll do my best to make this work. You guys see what I've kind of done here? Put that red line right on the black line. They're the same line, aren't they? So this is going to have multiple points shared. This is going to be the one that's called that consistent system. Not parallel, but a consistent system. Multiple points shared. So you would say that there is many solutions to this because many points or multiple points, if you will, are shared. They're going to go on forever. If it's one line on top of another, this is going to continue to go that way forever, and they're all shared. Okay. All right. So guys, choices on solutions for systems of equations. We might have a case where we've been getting solutions all the time. We've been practicing that. We're really good at this. Things that are new today. We're going to run into a situation where, hey, there's no solution. We'll show you what that looks like algebraically. There's also going to be situations where you're going to end up with many solutions. And I'll show you what that looks like algebraically as well. So kind of your cheat sheet at the front, kind of your background of stuff that you need to know. How are we feeling about this? Good? All right. Here's what I want you to do. Go to the second page of our notes. And I'm going to look at solving systems of equations. Now, guys, I'm going to throw these in decimals. And before we even find a solution to this, I'm going to look graphically to know what type of solution I have. And then we're going to show you what the work looks like. And we're going to make some connections between your final solution algebraically and compare it graphically. So what I want to do is have you jump into decimals here quickly. Maybe. All in decimals. All in all decimals. Yeah.
Used to come in and have this big like hat thing, and she would make me take it off.
Really?
She hated it.
That's too bad. That's too bad.
He'd sing that type of Mariah and she'd get so.
Maybe I'll send her that in a text today. I will. Maybe at the end of class for mine. Okay, guys, in example 1, what's the first equation that they're asking us to put in? Y equals what? 3x plus 2. All right, I'm going to type this in. I'll ask you a few questions about this. Here's what appears to be happening here graphically. Looks like they're parallel, right? Looks like to me then solution, many solutions, or no solution? No solution. Okay. We've got a great visual. We get that visually. Let's show you what this looks like algebraically. How can I show up a system is going to have no solution algebraically? Well, Guys, solving a system, your three methods, graphic, we just looked at that. We know what's going to happen here. We also have substitution. Is there a situation up there where one of the variables is all alone? Could I substitute then if one of the variables is all alone? Okay, I'm going to look at this top one right here. Y is equal to that mess of 3x plus 2, right? So what can I replace this y with in the second equation? 3x plus 2. So let me show you what happens. I'm going to rewrite this second equation. I'm going to rewrite this second equation by replacing this y value on the bottom with the 3x plus 2 up top. So the new equation I end up with is 3x plus 2. Oh, come on, work. 3x plus 2 equals 3x minus 1, like that. Guys, variables on both sides, we need to get rid of them, so what am I going to have to subtract? Well, let's not do that yet. Let's get rid of the 3x over here. Let's subtract 3x from both sides. Now, guys, we talked about this in the past, solving equations with variables on both sides. There are times that when I get rid of the 3x on the right, it doesn't just drop out of one side. It potentially could drop the x's out of how many sides? Both. What's going to happen to the 3x's over here on the left? Gone. What's going to happen here? They're gone. And we end up with a statement, a comparison of two values, if you will, which states that on the left side you're left with a 2. What are you left with on the right side? If the variables fall out, something weird is happening. And when something weird happens, we may get a solution, we may not get a solution. Talk to me about the validity of that statement. 2 equal negative 1. True or false? It's very false, isn't it? Very false. If you ever end up with a situation where variables completely drop out, you end up with a comparison. One number on the left, one number on the right, and that comparison would be false. Well, shucky darn. If that's not going to work for us, we got to say, hey, there's not going to be a solution to this. So do you understand how this work right here ties into that graph of parallel lines? Are we okay with that? You end up with a false statement. This implies no solution. Oh, why is this so choppy today? No solution there on that. Okay? No solution.
It should be like that.
Yeah, it should be. I think my battery is kind of dying. All right, so let's look at another one here. I want to do the reverse order here. I want to solve this one right here, and then I want to use decimals to verify stuff. Okay? So guys, looking at this one right here, any variable all alone? Is there a variable all by itself? Could be. The x could be. We could very easily get x all alone if I want to do that. I'm going to use the elimination method on this. Is that okay? All right. Stay sharp on all of your methods. Let's see. The x's and 4x, they don't match. The 3y, the 2y, they do not match. So we're going to crisscross. So what am I going to multiply everything up top by? 4. How about on the bottom? What do you want to multiply the bottom by? 1. Okay. So let's rewrite this. This one right here is going to become 4x minus 12y. All agree? What's that going to equal? Equal 24. How about the next one? Once you have negative 4x plus 2y equals 6. So right here, guys, we have the 4x is the same coefficient-wise. How about the signs on those coefficients? Opposite or identical? Opposite means to add or subtract the equations. Add them together. Let's roll. Quick question here. When I add everything, negative 12y plus, minus, no plus, right? Yeah. You want to add all these together. So negative 12y plus 2y, wouldn't that be negative 10y, kiddos? Yeah. Did the variables completely drop out this time? Yeah. If the variables don't completely drop out, are we going to be able to get one solution then? We will, you bet. How about the 24 plus 6 on the right? What is that? 30. What's that make our y value? Y is -3. All right, so since y is -3, I need to come back to the original equation. I prefer the first one of the original equation. What do you want to substitute for your y value? Substitute -3. So here we go. Put the work for that right over here. There we go, x minus. How about 3 times -3 right here? What would that be? Or if you will, right here. Isn't that really a -3 right here in the problem? -3 times -3 would really make this x plus what? To equal 6. It's the goofiest looking 6 I ever made. What's that make your x value? Very good. X equals -3. So in this situation right here, we solve for x, we solve for y, so that is an ordered pair. What's your solution here, gang? -3 comma what? Okay. Somebody verify that graphically. Jump into decimals, type those two equations in exactly as I had them in decimals. See if they cross it. Who's into decimals right now? Somebody want to punch those two equations in for me right there? Jarrett, you want to punch those in for me? X minus 3y equals 6 in that first field. And then the second one, -4x plus 2y equals 6. Jarrett, do you have two lines that cross, first of all? Go hover above the point where they cross. Does it kick out a value to you when you hover on that or click on that? Does it kick out -3, -3 to you? Okay, so we know we're right here. Taryn, question? First one was substitution that we used. Okay. So guys, I thought this one, I think I obviously made a typo on this right here. I wanted this to have many solutions. So I'm going to change example 3 up here a bit. I'm going to change example 3 up here a bit. Let's do this. Let's call this x plus 2y equals 20. And I'm going to call this -3x minus 6y equals -60. Okay, so let's work with this one right here. Okay, so I don't have a variable all alone, so I don't want to substitute. I'm going to go right into elimination since I don't have a variable all alone. And then the next one would be this. Any variables exactly the same coefficient-wise? Okay, so we need to crisscross. What are we crisscrossing with up top? What are we crisscrossing with on the bottom? All right, so let's rewrite this. Guys, help me out. What's up top now? What's up top? If I multiply everything by 3 up here, what's the top equation going to become? Yep. Yep. How much? Very good, Chelsea. Let's see. I think I can handle multiplying this by 1. You guys check me on this? I think it's -3x minus 6y equals -60. Okay. Adding or subtracting? I'm going to add, right? 3x plus -3x. What is it? 3x plus -3x. What is it? It's gone. 6y plus -6y. What is it? It's gone as well. So what do you have on the left here, guys? Everything kind of cancels here. What value were you using, McKenna? What value were you using? 0. What are you going to have on the right side? 0 again. Quick question. Any variables remain in that? No, variables are gone. However, that compares comparison in the very end. That comparison in the very end. A true statement or false statement? True. What do you think this is going to imply? What do you think this is implying? At least one, right? How about many solutions here? Many solutions right there. Yeah, check it out here, guys. Check this out. This is pretty cool. Let's jump into decimals again. What were the two equations I put in there? Was the first one x plus 2y equals 20? I'm going to zoom out a bit so I can see this. All right, so the green line right there, guys. See the green line? That's the x plus 2y equals 20. What was the second equation? It was negative 3x. What was after that? And what was the value? Negative 60? Whoa. What just happened to my green line that was there? It turned purple. Green line. Green line is there. Purple line is there. They're the same line, aren't they? What kind of system is this called then if one line lies on top of another? What was the word we used? Consistent. It's a consistent system, all right? Great. So we can either have one solution, no solution, many solutions. I think we've got the characteristics for this question so far. Yes. Second example is one solution. Anytime you get a point or an ordered pair of two, like 5 times 7, that's considered one solution. That's the one point that those two lines share. Good question. All right, let's roll on to that last page. Get this knocked out of the park, and I'll leave you alone for the rest of the day. All right? We all have one trimester and 1 day in the books, which makes us school here about 34% of the way over, which means you only have 66% of the way to go. That's like a standard bell curve. Never mind.
Yeah.
You guys must think I'm crazy. Is that what you really think?
Just a little bit.
Just a little bit?
Yeah, you guys lost a little bit.
All right. Rules to determine if stuff is going to be consistent, parallel, or cross. Here's the deal. Guys, I'm just going to throw some rules up here, take them for what they're worth. But, guys, when we had a situation where the number of solutions was 0, what kind of lines do we have when there was no solution? Parallel. And what's true about the slopes of parallel lines? They're the same. All right? Now, talk to me about the y-intercept of a parallel line. Do parallel lines start at the same y-intercept, or do they have different y-intercepts? Different y-intercepts. So I'm going to say if you have a system, of equations, if you ever have two lines where if you put something in slope-intercept form, if the slope is the same and the y-intercept is different, this is implying what? No solution. Okay? The only thing you need to know about equations that have one solution, the slope every single time for one solution will be different. Lines with different slopes are always going to cross somewhere. A line with a different slope is always going to cross somewhere. Okay? You don't need to know anything about the y-intercept. If the slopes are different, you're going to have one solution. Okay, and then this idea of two solutions are meaning many, two solutions or more right there, meaning many. That means one line on top of the same line. It means it's the same line, right? So what has to be true about the slope? Same or different? Same. What has to be about true about the part where they start? Same or different? Same line has to start at the same spot. So I'm gonna do something here quickly. You tell me 0 solutions, 1 solution, or many. You ready for this? Now, conveniently, I've put both of those in slope-intercept form for you. I want to know, is that going to have a solution, 1 solution maybe? Is it going to have 0 solutions, or is it going to have many solutions? I'm hearing a lot of zeros already. What's your argument, Gavin? Okay, so right here, slopes are, they're the same, aren't they? Both are the same, 6. Same slope. How about your intercepts? Same or different? Different. Let's see. Same slope, boom. Different y-intercept, boom. How many solutions? No solution, right? You understand how to read this chart then when I ask you that question today? No solution. No solution. Perfect. Got one example here, and then you guys can get rolling on that new assignment. Any questions to this point? Anybody? All right, let's get this last one done. I need to do some labeling on the diagrams here quickly. Go ahead and read through the wording up there, and I'll get you the values here that you're going to need. All right, gang, here's the situation. In this real life example right here, we've got the perimeter of a trapezoidal piece of land, okay? Maybe you own some land, and this is what they're property taxing you on, okay? Property taxes. They don't pay me to upkeep my land. Why do I have to pay them to have the land? I don't get it. I should start charging the government every time I mow my yard, because they're charging me taxes on yard that I own, right? So I'm maintaining their yard, so I should charge the government for mowing their yard, right? Am I right?
Yeah.
Yes.
That's why I'm running for president in 2016.
Yep, Donald Trump.
Okay? Oh, I
Right.
wrote.
Or Ben
Yeah.
Carson.
You don't want to bring either one of those names
Ben
up.
Carson
Okay?
is a joke.
Let's leave the circus party out of this, all right? Let's leave the circus party out of this. Bunch of clowns every time. All right?
There's no
Hey, there's a couple words going on up here. Perimeter of trapezoidal piece of land. Perimeter. Remind me what perimeter is again on any kind of polygon. The distance all the way around something, right? You're told the perimeter of this trapezoid right here is how many kilometers? You're told the perimeter of the rectangular piece of land is 216 kilometers. It says write and solve linear systems of equations to find the value for x and y that would satisfy this condition. All right, so let's come up with an equation for the perimeter of the trapezoid first. Guys, I'm going to start with the x's. Looks like I have a 2x on the top base and 4x on the bottom base, right? So combined, what would that be? 6x plus how many y on the trapezoid? 12y. And what's that going to equal for a total? What did they tell us our perimeter was, kiddos? 72, right? Okay, so that would be an equation for the trapezoid that models the perimeter of that trapezoidal piece of land. So you guys tell me what the equation is going to be to model the perimeter of the rectangular piece of land. 18x plus 36y equals, what was the perimeter of the land of the rectangle?
216.
They had asked us to say, well, we'd kind of like you to go through. We'd kind of like you to go through and find values of x and y that would make this true. Okay, no problem.
So to get your 6x, you took 4 times.
Yes.
Okay.
Now, guys, some of you have recognized right off the bat that none of this matches here. But some of you might say, well, look at the 6x. How could I turn that 6x into an 18x? I can take everything times 3. Now, I've been saying or recommending crisscrossing, right? I'm gonna go ahead and crisscross again, but if some of you guys can recognize multiplying the top one by 3 would get you 18 x's in both, go ahead and do that, all right? If I use that crisscross method like I've suggested, I'd have to multiply everything up here by how much? 18. What would I multiply everything down here by? Now another way to do this is the following, guys. After you crisscross, can 18 over 6 be reduced? What's 18 over 6, or 18 divided by 6? 3, right? That would be like multiplying the top then by 3 and 1. All I did is kind of take that 18 over 6 and reduce it. Do you guys see that, how that works? So I'm going to do that quickly. I'm going to multiply the top by 3 and the bottom by 1. When I multiply the top by 3, here's what you get. You get 18x plus 36y equals 216. Boy, I've got a little deja vu going on. A little deja vu going on. If I multiply the bottom by 1, after I've done our crisscrossing in simplest form, what do you notice about those two equations I'm about ready to apply elimination to? They are exactly the same. And when I go ahead and subtract, what's going to happen to everything? What are you going to end up with on the left? What value are you going to end up with on the left? 0. Both variables are dropping out, right? 18x minus 18x. Yep, subtracting because the 18x's are the same sign. You're going to end up with nothing on the left. What's 216 minus 216 on the right? No, 0 again. So this is back to that idea. If all of my variables drop out in any process, you've got to go ahead and see if your statement is valid. 0 equal to 0. True that or false that? True that, right? If that's a true statement, what's that imply about the number of solutions then? Many of them. There can be many solutions here. There can be infinitely many solutions that work here. All right, so there's not just one answer to this. There are many solutions to this. Somebody give me a summary of what we discussed today. Summary of what we discussed. Discussed not being a character on Inside Out. How many solutions? What types of equations have we been calling this? 2 equations, 2 unknowns. Starts with an S. What? Similar? No. Look at your title on the front side.
Solving special system equation.
Whole idea is how many solutions do systems of equations have? They might have 1. We've explored that a lot. Today we found out that, hey, some of these may not have a solution, or some might have many solutions. So, questions about this?